Okay. Well, the first lecture, I was asked to really talk about really scanning probe methods, specifically on oxides, and that's also good because this morning we're going then more also into ferroelectrics and oxide materials, so not really too much into magnetism. And I'm coming really from Dresden. Also yesterday there was also already Stefan here from this beautiful town, like medieval town. And to give you really a feeling where this is, we are really located here just between Berlin and Prague, and this is very actually located at the triangle between Poland, Czech Republic, and the German. Well, what I will talk about today is really the scanning probe methods that we apply for really investigating on a local scale, getting really different parameters, because that's very important. We have macroscopic techniques, we want to grow something, but if you go nanoscale, it might be quite different, and you will see actually there will be a lot of differences, a lot of impacts actually on that. I would also like to really already advertise what is in the second lecture, that's actually on Thursday, because on that second lecture I'm going to talk about 2D electron gases in so-called domain walls. And we are really doing this, and you can see here an animation. This is actually domain walls really triggered by second harmonic generation in 3D in order to really get a full image, but that's actually just as a teaser for those ones who will leave today, for instance, like Vincent, and then missing this talk. Okay, so let's come back to what is actually the topic of the day, which is scanning probes and the local properties. And everything starts with these two guys, Gerbinik and Heini Rohrer. And these are really, it's a picture from 1986, just when they received the Nobel Prize for this kind of instrument, the scanning tunnel microscope. And I think everybody knows we had also very nice animations these days, actually, and really bridging the eyes towards spin polarized scanning tunnel microscopy. So yes, this is really working at room temperature as well, no problem. Okay, there are other issues on that. But I would like to start with a small take-home message for the students sitting here. This is never give up. And this goes exactly back to these two guys. And as you guys know, they got the Nobel Prize for this very nice instrumentation, which opened a lot of field in research on the nanometer length scale. Now, the point was actually that they didn't hand in their really work into Helvetica Physik Acta first, but they went to physical review letters and were rejected. The reviewers said, no way, this is all bullshit, sorry. So, because it cannot be that you can have a quantum mechanical tunnel effect on that length scale. You're scratching with your tip in your samples, and that's it, finished, rejected. So they didn't give up. So they've gone for that, and this is exactly why the first publication, most is 1982, is actually in a Swiss journal, Helvetica Physik Acta, and hence not really actually something that actually has been published really at highly ranked citations. But that's exactly the message. Don't give up. Even if you have some pitfalls or whatever, there's definitely some bright light at the end of the line, of the tunnel. So, is STM, scanning tunnel microscopy, able to do something also for oxides? And we do know that actually the tip that we see here mostly needs to use a conductive sample. And in oxides, we don't have too much density of states, that's clear. Wide band gaps. Brian says 3.3 for barium titanate. Is he somewhere? Right? Maybe. Okay, whatever. But that's exactly what the nice thing about STM is. We can see, so to say, the density of states on the wave function. I would like just to take one example from Sascha Repp in 2005, IBM results, where we have a molecule, which is actually shown here. This is, so to say, the HOMO, the highest occupied molecular levels. So just to get you familiar with that, we take all wave functions, we make a superpositions, and look up to which level we get, let's say, filled electrons, the highest occupied molecular. So it's a hybridization of wave functions. And similarly, we can really do this for the empty states. And that's exactly what the HOMO-LUMO means for this molecule, which is a pentacene, 5 rings. And you see nicely that this is the experimental result, that these measurements here really reflect what the density of functional theory is really showing you. Fantastic, beautiful textbook example, really something for your lecture. Well, can we do this also on barium titanate? Can we really look with STM, which is looking on wave functions of barium titanate? So can we use STM for oxides? And the answer is, well, partially, I would say. We need the band gap, definitely. We have a band gap in barium titanate. We have a band gap in most of the oxides. And these go up really up to 9 or even 10 electron volts. Now, one of the early works was really actually in the group here, where in Neddermeyer in Germany. And they were really looking at barium titanate 111 with a scanning tunneling, ordinary scanning tunneling microscope. You see the parameters, 2.2 volts, and that's even below the band gap of barium titanate. And the currents they were really driving was 0.1. Plus means sample positive bias. So sample positive means the electrons are injected into the sample. Now you can nicely see this is one of the first scans I did, and if you look on these and you see these lines, you see these kind of really sausages, I would say, rather, actually, but look really striations, and these are all parallel to the scan directions. They interpret this as islands or whatever, different regions. The answer is, this is fully insulating. So the interpretation that I did at that time was really wrong, simply because you should be really aware of and really skeptical. If you have lines like this parallel to your scan direction, you should do something, scan, orientation, whatever. And you can see that also in the zigzag. This is charging up with the tip of the sample. So they zoom in even on these areas, and you see very nice reconstructions. A reconstruction is a superstructure that on 4 unit cells of the barium titanate, you get only 1 atom. So you get a 4 by 4 at 1,500 Kelvin. They heat it up to 1,550 K, get a 3 by 3 on the superstructure. But this is all not barium titanate. It's all barium-rich oxide deficiency. So what you do by heating, so to say, you get rid of the oxygen and hence you reduce the surface. And that's why the band gap is reduced and hence the STM can see something. No way. This is not barium titanate. Wolf Wiederer later wanted to also continue on this and said, okay, let's take thinner films, just 1 to 2 monolayers, unit cells of barium titanate on a platinum substrate. Well, surely this is actually something, if you have really an oxide, you can tunnel through. This is enough really. And hence, what you get is actually the following, that on this substrate you get even a compression of that film. So compression means you get a piling up of the polarization along the Z direction. That's exactly what you see. They miss to give values because they can't. They can only really tunnel through, nothing quantitative. And on top, it's also a superstructure, and you can see nice pictures, but that's it. Nothing quantitative. Okay? So at the same time, basically, back in 1989, Greg Kochalski had an idea and said, well, why don't we use the STM at a higher frequency? Because so far, Binnig and Rohrer said, well, we are going to apply a DC voltage. Why not to apply an AC voltage? And in fact, what he does is actually applying something like 2/3 of a gigahertz or 1 gigahertz, as you see here. Very high, actually, frequencies. And if you do so, he says, okay, we're going to double this. We're going to make a nonlinear scanning tunneling microscope by doubling or tripling the frequency between the tip and the sample. So this was the very first example, basically, where you have an AC system working, and he was really publishing this. What about the results? You see, actually, this is a copper oxide surface, so we're talking about oxides at 1 gigahertz. Okay, it's pretty rough. The resolution is pretty well. He goes and tests this actually with aluminum oxide. Everybody knows we have an oxide surface, 3 nanometer thickness of the oxide on aluminum, spontaneous oxidation. And what he measures is something like 50 nanometers if he looks on the first harmonic. And if he looks on the third harmonic, he gets something like 20 nanometers. So this is not quantitative at all, but it's a good example to show of never give up, because actually simply he's trying to test this at higher frequency. And you will see actually during this lecture, going for higher frequencies is not only to probe different properties, but also some kind of way out. So Steve and Paul Weiss here were trying then to measure on pure glass. You take a window glass, crack it down, put it under the microscope, and that's the result. Looks like the Swiss Alps or the French Alps, but it's nothing really quantitative that it can deduce. Maybe you can publish, and they did, but that's it again. So STM is not of big use. And hence, we have to really go and really use something more delicate, which is a scanning force microscope, mostly driven by this guy, Christoph Gerber, the same year, 1986, when the Nobel Prize was awarded to Binnig and Rohrer for their STM. And what we have these days, and I think Karim introduced already very nicely, is actually we have a cantilever, and most times actually we're going to really measure this deflection, so to say, of this cantilever by a beam. I do have also some experiments here, and you will see, I will use them during the lecture. I have a cantilever here, you see that here? You can see that well. So I can also do some dynamics and so, I can do some tip crashes. There's no tip here. Okay. And the way you do this, basically, you have your laser point on the top, and possibly you can see that. No, you can see that. It's too much reflections. Okay. So whatsoever. This is actually the basics at the starting point of scanning force microscopy. Well, the nice thing about an AFM is we're sensitive to any kind of forces. So that means we can really measure tons of interactions, not only the electrostatic interaction that an STM is really measuring, but we're sensitive to everything: optics, local scale, chemical forces, long range, van der Waals, or even magnetic and electric forces, and so on, spin interactions. So this is the good thing. We're sensitive. The bad thing is we're sensitive to everything. So that means at the same time we have to differentiate. What are we doing really? Okay, this is exactly the challenge that we face here. And that's exactly what I want to really drive with you with, is to show to you, if you really dedicatedly actually address certain frequency ranges or certain methods, then you have tons of parameters that you can really measure with this kind of mimic. So let me show you here. This is actually simply a summary of what this tip, so to say, always is experiencing. Van der Waals forces are quantum mechanical, let's say, induced dipole interactions. So what is important to memorize now is, for every force, what is the range of interaction, A, and B, what is the decay length of such a force, actually, with respect to the sample surface. So if you pull back your tip, for instance, from the surface, how fast does such a force decay? We have very short-range chemical forces, being exactly what Dennis was showing before, the overlap of orbitals, right? So if we want to measure them, we have to go very close, which is on the scale of 0.1 nanometer. Van der Waals forces are longer ranged, electrostatic magnetic forces are even longer ranged, and optical forces, optically induced dipoles, are simply dipolar forces at different frequencies, higher frequencies. So we have both in the spatial and the time or frequency domain tons of ideas how we can really separate that. Well, this is the cartoon basically of what we have now. We have a force, we take an attractive force, we take a repulsive force, and the question is now, how can we really dedicatedly really address different parameters? We want to measure something quantitative on the nanometer length scale. Can we do that really on the repulsive part, or can we do that also on the attractive part? And what has been established so far is exactly that we are taking a tip, well, we're taking the cantilever, and in the first case, basically, we were just taking the cantilever and we just compress that really hard on the surface. So we really pressing, and you see nicely that also my cantilever now is really bent, I would say really convex, as you see here in the projection, hopefully. In the other case, if you want to really measure attractive forces, well, these forces are really much more negligible. These are very small forces, and hence what we have to do is some tricks, which is a dynamic measurement. So we go and do the following. We're going to vibrate the cantilever at a certain frequency. That's the frequency omega 0, its eigenfrequency. And hence what we measure is not the force, but rather the force gradient, dF over dc. And hence what we are looking at is really the frequency shift of this one. So this is exactly the frequency shift we can really look at. And in order to really get you familiar with this, I want like to circulate this experiment. I cannot show that here because it's, oh, maybe I can. I don't know. The frequency shift is a very sensitive measure. If you look, basically, can you see the small cantilever here vibrating? Well, maybe. Up is better? No. You can see that vibrating because there's an interaction. And if you really go for different interactions here, you can see that the frequency changes. So I'll let this circulate. You play with yourself and basically give it just a round. Yep. Okay. So we see who are the experts here, okay? Fine. Okay. So this is simply to differentiate between different types of forces, but different regimes. And now let me see actually whether we can really do something really more quantitative on this scale. And that's exactly what I want to really discuss with you. We start really slow actually on Piezo response and really pull off forces. And I think Karim already covered this PFM stuff a little bit. I will then go into non-contact regime, which is exactly Kelvin and optical forces. We will come into negative epsilon materials, metamaterials, and finally, I would really quit, if there is time, Mr. Chairman, by time-resolved scanning probes. So that means we can really speed up the scanning probes. Let's make a question. How fast do you think can scanning probes measure? So what is the fastest thing you can measure with a scanning probe instrument? Question to you. Numbers? What do you think? Huh? Who? Just speak up louder.
The time scale?
Or the time scale, yes? How?
Minutes.
Microseconds? What? Or milliseconds? What did you say? Milliseconds? I couldn't really hear it.
What is one scale?
Yeah, no, let's say, if there's an interaction locally, so to say, and you want to measure an interaction that is really time dependent, are we able to track, for instance, interactions on the picosecond length scale or on the millisecond length scale or on the microsecond? At one point, yes. Say again? Around. Exactly. So, in principle, so to say, it's possible to really mimic and to really make that really very fast if you have the right electronics and the right really mimic to that. So, this is exactly which has not been done too much, but which is exactly the way out for measuring parameters. So, let's start with the lower hanging fruits. And that means really we go into the contact areas. That means we go to the first part and we want to really look on, just review on PFM, actually what Karim was already really covering a bit. And I would like to break the ice to really memorize with you this name, Kurt Franke. He is actually the father of PFM, so to say, because back actually in the 80s, he had an idea to say, well, why not to apply to the cantilever a voltage? So he was taking this cantilever, and he was saying, okay, let's put up a voltage to this cantilever. Huh? So if you can please hold this line, okay? So basically, you're my voltage source now, okay? So instead of only doing, let's say, okay. Okay. So instead of only doing, let's say, a contact experiment, he said, okay, why not to apply any kind of very low voltage forces, which is a DC force, and an AC force typically 10, 20, 50 kilohertz. So that's actually the idea of Kurt. At that time, nobody was calling this piezo response. Thank you. You can release. I will need you later. So at that time, nobody was really thinking of really calling this piezo response because the effect was not clear. So he called it voltage modulation, force microscopy, something like that. So what is the issue? We want to really measure by applying an AC voltage to the tip both vibrations, which is inverse piezoelectric effects, vertically, horizontally along x direction and along the y direction, which is difficult to show because it goes into the plane, which is the whiteboard. Now, Markus Applenaub in my group, he did in 1981 the very first in-plane measurements by combining this method with the in-plane method. We were looking on friction signals and found, okay, there's a nice contrast on barium titanate because we have on the one side C domains and on the other side we can see the A domains. So they go elegantly together. And if you combine this with the third property, which is the Y direction, we found out that we can really do X, Y, and Z direction together. Now that's exactly something I call X-ray. Because in X-ray what you do, you take a sample, even if it's polycrystalline, and you want to deduce the crystallographic orientations of the sample. You want to really measure, is this macroscopic or as an ensemble 111 or 100 oriented, or is it 200, and so on. Now we can do this also with PFM on a very local scale, and the resolution is not bad, 5 nanometers. So that means we can take a sample, and this is actually a barium titanate ceramic sample. That means we have grains, and they're all different oriented in this kind of ceramic. You use this basically for piezo actuators. And we zoom in on a small area like shown here, and do exact this kind of X-ray or this tomography along the PX, PY, and the PZ direction. And you can recombine. We do also a quantitative measurement in the sense we calibrate that. We take barium titanate, single crystals as a calibration, and so you know PX, PY, PZ quantitatively. You can combine this in a picture, and in the end, what comes out is clear that your grain that you have been choosing has a certain orientation with respect to an outer XYZ plane, or let's say orientation. These are the so-called famous Euler angles. So this means actually we can really do this kind of X-raying for every such grain. You can do that on any sample. The only request here is to have a certain crystallographic grain. And as I said, the minimal size at the moment is 5 to about 10 nanometers. So you have a small sample and you cannot do any kind of other methods in order to really do some kind of macroscopic measurements. PFM can do it. Well, this means we are sensitive here to the parameters, the piezoelectric constants Dij. And as you know, these are tensorial properties, and exactly what we do here is measure these things. So this is one parameter that we can really quantitatively deduce from this measurement. Next, we combine this PFM method with pull-off force. What is that? So we again do the same thing. We take somebody that has some voltage on, and in contrast to be really doing the PFM measurement on the curve, we pull back now this cantilever while he's having his voltage on. So we do this, okay? Now imagine he's so strong and has so high voltage that my cantilever is charged, and that means basically it's rather glued down, and basically when it's flipping off from the surface, so to say, it's really pinned, and then actually snaps back. Thank you. So this means we can combine the picture that we have inside the sample, PFM looks, so to say, near surface areas, by what we actually measure just above the surface by pulling this off as a function of voltage. And we did such an experiment with PCT, 5347, and it's clear. If this is a ferroelectric sample, we have different properties already at the surface. For instance, we have charges. It's clear. Every surface, every oxide can charge up on the surface. There could be reconstructions, that mean there can be sparse charges. There can be polarization. There not necessarily need to be polarization. In a ferroelectric, yes, we believe there is polarization. There can be screening charges. There can be trapped charges which give rise to an internal field. That means simply that we believe that the sample has an internal voltage. And there's even more. There's inverse piezoelectric effect, which is affecting our measurement and so on. So it's a complex system. But we want now to measure this. We want to quantitatively disentangle at least these parameters. And how can we do this? Exactly by combining these two methods. Why is this possible? Simply, imagine he's going to turn on his voltage, right? And then the charge rho goes up actually at the surface. Huh? So that means the polarization doesn't change, not necessarily. There's a small change, we know. But let's stay for the first part actually in the linear regime. That means the only thing that happens is actually this, the charging of the sample is different. And this is true for every oxide. You can charge up the surface. For instance, you make a gate or whatever, and then hence the surface charges are increasing. Now these two guys, PZ and rho, they are contrary. On the one side, in PFM, we are going to have them balanced off with a minus sign. So basically they subtract each other. Now, by pulling off from the surface, they add up, simply because we are external to the sample. And that's good now, because now we have a possibility to disentangle who is who by rho, by PC. And this is exactly what we did here. The measurement curve as a function of this DC voltage, he's the DC voltage guy, huh? This is exactly shown here, and we pull back and we make the measurement, this is the measurement, and then we can really do the math behind this. Disentangling into PC, this is actually that contribution that comes from polarization, and that's a contribution that comes from surface charges. So this is a special sample, 5347 PCT, but you can take any sample in order to really measure quantitatively what you have there. We find here, for this sample, a polarization of 0.2 amps per meter squared. We find charge synthesis, which is pretty zero, as you can see, very flat. So that means whatever voltage, at least positive voltage we apply, there is no charging. Only by negative charges, below minus 20 volts, we find actually a linear increase on that, and hence we can quantitatively actually measure this. More of that in our model, where we just interpret this as a capacitor, right? We find also what is the dielectric constant at the surface. So imagine the cantilever, 0 hertz, 0 volt. We want to simply know what is the local dielectric constant of a sample. A unique question that we always have. Well, our tip is measuring locally. That means we find only the very local surface dielectric constant, which is typically for this sample 320. And you see, if you increase the voltage to 45 volts, actually this dielectric constant is really shrinking down. You see actually that this is the measurement curves as a function of voltage. It's really symmetric. It doesn't really matter whether we apply positive or negative voltage. This one is normalized to this 320 value, and hence it's really going down. So you should be aware when you do some measurements A voltage can always change the dielectric constant, and hence you have completely different values. In that case, actually, even a factor of 1.2 changes. We can do more. Since we do PFM, means we have a 10 kilohertz frequency for PFM at the cantilever. That means we can also measure what is actually that dielectric constant. Now we have a penetration, typically 50 nanometers into the sample. We measured this with inclined domain walls, by the way. And hence what you simply measure there is a much larger dielectric constant. So that means we have all these values, and you can really quantify them on the very local scale. Local means as local as the tip is. And the last item that we have found here for this sample is, yes, there's a bias field that is plus 0.44 volts. So in summary, also this kind of combination between PFM and PFS allows you to really go to quantify all these values, the polarization, density, internal voltage, surface bulk, and so on. Beautiful. Now, as you also might have read in the abstract and what I just was telling you, we're always talking about this dielectric constant, and now we come basically to the two most important parameters that we want to measure for any kind of material. This is the dielectric constant on the one side. This is the mu, which is the magnetic susceptibility for the other one. So what we just did is actually measuring really materials like ceramics, like your coffee pot, which is actually large epsilons, and the mu of all these materials is typically 1. We could also go the other axis. We could go up here to the iron, so to say, and really measure larger mu's on the other side, which is much more difficult to do, and which is more into magnetism. And I, for this lecture, didn't want to go too much into magnetism. But what we can do also is go negative in epsilon. We want to go negative here below the 0, because epsilon per se is not bound to positive values. It can take on any values. And the same is true actually for the mu. The mu can also take on any value. It can be positive, minus infinite, plus infinite. And in fact, there's a very nice paper by Veselago from 1968 who was saying, well, the electrodynamics for even negative values of epsilon and mu is very interesting. And this is something that has been really, until the year 2000, very much overlooked. So why not to go and really redo that at really negative epsilon values? Well, we will come to this and see metals like gold, like silver, or every material, even barium titanate, even any material can be driven into a negative epsilon regime. This is interesting. I want to prove this to you, that we can really get negative epsilon values as a specific frequency for all of these materials. Well, the dielectric constant, epsilon and mu, they go together, as we know, into the n squared. So if you take the product, you get what we call the complex refractive index. So since epsilon and mu are two complex values, epsilon prime, epsilon 2 prime, it also means that if you do this product, you calculate that, you get a real part that we call regularly the refractive index, right, n. But also we get an imaginary part, which we call the losses, the kappa. So there are two values. Stefan was calling them sigma 1, sigma 2. So there are different values, and the question is simply how you look at these at different frequencies and in what regime and what history you come from. So this is important now. So this is all determining, these values are all determining the physical properties also in an optical regime. And hence, since we're talking already about different frequencies for these values, you nicely see actually that at different frequencies we can really figure different excitations, dipolar orientations. We go to microwaves, or we go to atomic, really terahertz excitations here, and we go, last but not least here, to electronic transitions. So wouldn't that be nice that our scanning probe would be able to really measure all of these? And you see what the challenge is now to go really and address all these frequencies with scanning probe. How can we do that? That's really a tricky thing. So these are really now higher hanging fruits, right? So we have to go and really grab those ones, the higher hanging fruits. But I'm really very much confident, and you can trust me, there's good ways out. So we go and basically track this simply by taking the attractive part of the scanning force microscopy curve. So you have seen that before, and you remember we do a dynamic measurement here. That means we do a dynamic measurement at a frequency omega 0, which gives rise to a force gradient, and hence we can really track this. And we can track this very accurately, simply because it's a nonlinear curve. So let's look on this kind of dependence here. Let's take this van der Waals curve, and we know van der Waals interaction goes with 1 over r power 6, right? Independent of whether you take permanent dipoles, whatever you take, it's always a nonlinear curve. That's good. That's good, in fact, because if it would be linear, and you have your cantilever oscillating in this kind of linear field, I don't need you to say, okay. If you have a cantilever linearly oscillating, this would mean that actually we get a response exactly at this oscillation frequency, big omega. Now, if you do the same thing and you oscillate in a nonlinear field like this one here, it's quite clear what you get. You get a Fourier series of frequencies. That means a first amplitude peak at exactly once the resonance frequency, then twice, the third, fourth, and so on, at infinite really wavelengths. So what we do is actually we disentangle this kind of modulation, this is the in and out actually of the AFM, into higher frequencies. And you can do that now for every measurement, whether this is a magnetic or whether this is a dielectric or whether this is even an optical measurement or a microwave measurement. So what you're looking at are really higher harmonics of the cantilever oscillation and even sidebands of those ones. And in order to really show you how this goes, I hope this small experiment is really meandering around. We see exactly this cantilever being excited. So we have a shaker here. That's the basic setup that we're using in our microscopes. We have a shaker here that drives exactly the resonance frequency omega 0, let's say 100 kilohertz. And we measure this with any kind of mimic. We had this beam deflection before. You can take interferometers. And now comes the important thing. What do you do with this kind of information? The first thing is actually we can measure this frequency shift and take this to make simple topography images. We can make exactly with the same signal magnetic imaging simply by retracting the tip but looking on the frequency shift. But then we do a trick. We apply on the first thing also an AC voltage between this tip and the sample. And that means now that actually my voltage source is no longer DC but can be anything. It can be microwave, it can be optics, it can be anything. So basically, when he's basically applying the voltage here, you see nicely that we get sideband modulations of this kind of 100 kilohertz modulation, which gives us an information on electrostatics or even on quantum capacitance. I will show this to you, how this works, because that's the basic principle of the sideband modulation and how to retrieve quantitative data. Moreover, there is more there. You see that this cantilever is oscillating, and as you see, if I'm going to oscillate, and if I'm not oscillating anymore, you see the stamping is very fast. It's even half a second for the stamping. So this means we have always dissipation. Now, can we cope with that? Because this dissipation is a very important source of information. So imagine we take this cantilever, we oscillate it, and then we have a feedback loop. You see this here. That goes on the drive that says, hey guy, I want to maintain always the same oscillation. And in this case, that's me. I'm the drive at the moment because my hand is really shaking so that the oscillation amplitude is always the same, maintaining the same amplitude. In our case, this is very small, 2-3 nanometers only, but you have to feed back this. And this is exactly how you can really furnish your oscillator in order to really maintain the same amplitude. Why is this important? Well, because with this STM you can really measure different interactions. Let me show you. Okay, I forgot about this one. We can even add light, whatever, at terahertz or infrared frequencies in order to really make an illumination and hence induce dipoles. So now it's no longer van der Waals interaction, dipolar interaction, but now it's an optical dipole at a microwave frequency interacting with your sample at the microwave frequency. So you can tune, so to say, this kind of sideband or interaction with anything you want to really feed in here. The importance of that one is the following. If you have an oscillator that is exactly shown here with its equation of motion, that's my cantilever, we have some damping, and you see basically that's my omega 0, that's really low or high for this case of cantilever here. In general, in our experiment, it's really low, so this damping coefficient in general is very low. And then we have the drive. That's me. And then on the other side, we have the interaction. The tip wants to measure something with your sample. Now, this interaction has so-called conservative and non-conservative contributions. What is a non-conservative contribution? Question to you. forces are conservative or non-conservative. What are non-conservative forces? You know that?
Friction.
Yes, exactly. Friction. Dissipation. That means simply that actually this is not an energy that we can restore or get back somehow. So it's really dissipated mostly into other forms of energies that are really not really coherently restorable. That means exactly that my force can be really divided into a conservative part, that's the cosine in your description, and a dissipative part, which is a sine. So as you know, mathematically, it's cosine plus I sine of a wave function, right? So that's basically exactly these two things that you can disentangle. You feed this back in, and you get two equations. One is the conservative equation here, and hence the delta F is a good signal to measure. Or you want to measure something like a dissipation, and then the drive signal, me, my hand, how much energy I'm going to really feed in is a good signal there. So we have everything at hand. That means we can really measure all the thing, and we can understand the system much more elegantly by looking really on these two signals here. To give you some numbers, because the dissipative part has been mostly overlooked actually in all of these experiments. If you have a dissipation, you just take the drive force times its velocity, you put in the values that you know, typically force constant 100 newtons per meter, resonance frequency 100 kilohertz, you get a Q value, we work in vacuum 10 to the power 5. The beta is a sample property, which means a convoluted quality factor oscillation stuff, which is typically, in our case, 0.1. We have an oscillation of 2 nanometers, and hence we have to drive. My hand has to really wiggle at 1 femtometer. And you see nicely what comes out. Very small energies. This is the resolution we have in the microscope. 1 attowatt. And why is this important? I want to show you all the possible dissipation mechanisms that you can really have. There could be intrinsic ones, actually through artifacts, or simply because you are able to operate your machine. There can be really different eigenmodes of this cantilever. There's not only the fundamental mode, but there can also be higher modes, as you can nicely see. So from that point of view, there can be different dissipation channels. There can be interaction, that's the one we are up to. There can be electrical dissipation, there can be magnetic dissipation, and so on. You see this catalog is so long, and very, very little has been done on this. So dissipative measurements is interesting, and I want to show you just one example of such a dissipation, which is skyrmions. So because we all measure the skyrmion stuff that we do in our MFM measurements, we do this all in this kind of dissipative channel, because that's much more sensitive than any kind of frequency shift, much more sensitive than any topography measurement. So what we do is all this dissipation. And you see, I hope this has been really covered last week, that skyrmions, these kind of really states can have different really forms. We can have, so to say, Bloch. This is actually what you see here, that the vector of spins is really turning. If you go and really walk through, let me do this for you. I'm going to walk through from here, and I'm going to be the spin, so my spin turns this way along the k vector, while in a nail skyrmion, as you can nicely see, it's really turning within the plane from this to an opposite direction, so it's really turning exactly what Dennis before was really showing in some of his cartoons. And then we have a mixture which is called the anti-skyrmion, that along 2 axes, you see basically along this axis and 45 degrees shifted, we have a combination of nail and Bloch. So what you see here is exactly such kind of Bloch skyrmions in a copper oxide selenide at 10K. This is the low temperature skyrmion phase. We see a domain wall in this GVS sample, and you see nail and anti-nail skyrmions on left and right. And we see anti-skyrmions here, so to say, in this room temperature material, which is called a half-Hösler material, manganese. This all dissipation. So we can measure this also by dissipative channels. So that was the only thing I wanted to really show about magnetism and also about dissipation. Now, we still have the problem. We want to go to these higher frequencies. How can we do that? We want to address these higher frequencies, and we have now the mimic. We know, okay, we can apply a voltage, we can apply AC voltages, we have this cantilever, we can oscillate this cantilever. How could that go? And I would like to basically really sketch this with a very simple, understandable experiment, Kelvin, which is naturally that we want to really measure something, which is something like the surface potential. We want to measure surface charges. We want to measure something like the contact potential difference. And we want to measure capacitive, quantum capacitance. But in contrast to before, now the cantilever is really away from your sample surface. We never go into contact. And I tell you this is good simply because, as you guys know, I like him very much, but he's a voltage source, right? So when he's a voltage source, he's driving also currents. And if I'm in contact with my cantilever, most of the time I'm charging up my surface unwanted. So I get also transport properties at the same time when I want to measure. That's why going back with your tip, really measuring in non-contact, as we say, is much better, because then you have only that stray field produced by his charges. And that's much, much more elegant. So let me show you how we can really do that. And taking this principle allows you now to go for any frequencies. I will show you it's going to be a sideband modulation. We're going to just track a sideband of the cantilever, and hence with this we have a very high sensitivity. Let's start simple. The cantilever now, here's the bias. He's going to really apply a bias, let's say negative, and hence we are inducing positive charges, which means we get a Coulomb force. If the charge here would be positive, it would be also a Coulomb force interaction that is attractive, simply because then plus the induced charge would be minus. So if you put this into a formula for this electrostatic forces, it will be definitely a frequency shift, delta F, which goes quadratic with the voltage. We're not sign sensitive, simply because Coulomb forces are always attractive. So that means if you want to really measure something like work functions or interfaces, charge transfer or polarizability in these samples, then this is not enough simply to really monitor that, this delta F. Let me show this to you. This is the curve that we have. This is the same formula like before. We have a parabola, and this parabola is simply given by these two terms, the DC voltage, and let's say the contact potential difference that we have between the cantilever and our sample. What is that, the contact potential difference? Well, two materials, as you guys know from the table of the periodic table of elements, they have always different configuration of electrons, right? We had the Hund's rules this morning, and hence we fill up all our electronic levels completely differently. That means chemically, or let's say electrochemically, there is a net potential. When you take iron and tin or whatever you take, you can always take two different materials. You will always end up with a certain voltage, or in electron volts, up to 5 electron volts differences. This means that this center not necessarily needs to be at 0, but can be shifted exactly with respect to this contact potential difference. So this parabola shifts, and you see what you can learn from this is exactly what is the contact potential difference, what kind of element do I have? You get element analysis. Well, we want to track this, and with this simple schematic it's not possible, so what we need to do is now to apply a modulation voltage. We want to apply, so he's now my source again, he's more functional now, he's a DC source and an AC source at the same time. He managed this. So from that point of view, we get actually modulation of the force by the total voltage, which now contains a DC part, but which contains also this AC part. Now how does this look like? Well, this means simply that in our parabola we're starting here, the modulation goes up and goes down again. That means actually we're starting here, and if you look on the phase, we're starting low, getting high, low, high. So that's exactly this signal. It's a nonlinear response, as you see, because this curve is nonlinear. This is good again, because nonlinearities, I like them, give us much more music in the world, in life as well, than linearity. So we are on the left side now of the apex, as you see. Now let's go to the right side. What happens there? Well, the same modulation. The only thing we did is he was cranking up the DC voltage, this one here, and hence we're shifting from the left to the right side. We have the same modulation from here to here, but be aware, we start up, we go down, up, down. So this is different. The phase has shifted by pi, right? This is important. That means we are sensitive really to the slope of this curve. And this is really unique, simply because we can now see, aha, I do have, actually I'm on the left side, I do on the right side, or I can go into the middle, where I have a modulation, so to say, that goes from left, up, down, up, left. So you see actually that frequency is doubled here, twice the frequency, that's one thing we learn, and we in the minimum here, that's exactly the point where we search for. Now, let's put this into mathematical formulas. You see in the mathematical formulas, what happens there is the following, that we get a DC term that goes really with DC voltage applied and the capacitance, the stray capacitance between the tip and the sample, that's it. Then we get a first order term at once F mod, and then we get a second order term at twice F mod. And if you do a development in a Taylor series, we get even higher terms. So that means actually, if you put this series into really a frequency picture, which is shown here, we have the frequency axis down here. Then what we have is actually we have a small modulation voltage at 2 kilohertz right down here. But we have my drive. This is my oscillator, 151 in that case here. And simply because he's applying a 2 kilohertz side modulation, we get also sidebands, F0 minus F mod, F0 plus F mod, and so on. We get higher order sidebands. And that's now good. The benefit that we get is the following. First of all, we're getting out of the noise. Mostly we are bothered with 1 over F noise, frequency noise, and hence what we have here is actually a signal that is fantastically clear and really crispy, actually, because that one here you see that you normally take, we call this AM Kelvin, is really low, buried in the 1 over F noise. No way to go. Here's an example of what the result is. This is exactly the sideband, and you see nicely this is on 153. It's the plus sideband, so it's F0 plus F mod. And we did the following experiment by reducing the voltage from 500 to 50 to 5 millivolts. Wow. And you see nicely, even at 5 millivolts, you see a very, very clear signal. So this is very important that you have a very good sensitivity. Why? Well, imagine you want to measure a semiconductor or any kind of surface, barium titanate, and you apply a voltage of 2 volts. That's typically what people do, 2 volts for the Kelvin. Then you're inducing so many charges in the system that actually you go over band gap sometimes, and hence you're changing the system exactly the same way as you're in contact with your cantilever. So this is exactly what we call non-invasive, that you have a small disturbation that is really so small that it doesn't really affect too much the other systems. Here's the proof. This is the picture. You see nicely on this molecular system, this is one molecule. It's 1 by 1 nanometer. It's called a tetrabutyl porphyrin. So we have a porphyrin ring here with 1, 2, 3, 4 legs. It's like a lunar lander standing on the surface. Whoops. And in the center, there's a copper atom. This is actually really good for doing really molecular electronics. And what you nicely see is that the topography image taken at the same time like this kind of sideband demodulated charge picture has a much lower resolution, while here we can see 1, 2, 3, all the 4 legs of this here. And we see even more, it's charged negatively. Black means negative, that means all the charges, electrons, sit in the leg and not in the platform of the porphyrin. So this is a quantitative now map of how measuring this surface charge potential. There's more to say. If you go and look, actually now look on the second sideband, which is the force gradient as we see here, what can we learn from that? Well, we had this actually in the formula already. This is at twice the frequency at the sideband, and you can nicely see that this one is now really sensitive to the DC over DC, the capacitance only. And it's fully independent of the DC, so we don't need him. Okay, I need him for modulation, that's good, but we don't need him basically for a DC voltage. It's fully independent. So we can also measure local capacitance. Example, graphene. We have here a couple of graphene flakes, 1, 2, 3, by optics identified. We measure them with the STM-F scanning force microscope in topography. In Kelvin, we do see, let's say, a small potential change. You see from 1 to 3, a change of about 0.15 volts, which is 150 milli-electron volts. So monolayers are always charged more negative. That's the answer here. Now, what about the capacitance? Well, we measure the capacitance of each of these layers. What is that? The quantum capacitance that we measure here. For this, we have mounted the sample, as you can see, also in a field effect transistor device. That means simply we have a gate electrode applying exactly the DC voltage, that's him again, and he's cranking up the voltage from minus 15 to plus 15. So imagine there's a field on your sample that comes up, and what does it do? It does produce charges, exactly the same way like we had before in the contact experiment with the oxides. So now these charges produce on the top of the surface and on the bottom of this graphene surface different charges. And hence you could nicely see that there's a huge difference at these charges. This is the blue for the monolayer, while the bilayer doesn't respond to this at all. It goes up linearly. So charge differences on two plates of a capacitor is nothing else than you build up a capacitance. And that's exactly what you see here. So we track this second order sideband, and exactly what you see here at the crossover, at the 5-volt bias, that exactly here we have, so to say, a balanced quantum capacitance. We are able to really deduce the value of this capacitance of this kind of graphene layer. So what are the parameters we can reduce here? Surface potential, density, we have contact potential difference, we have this capacitance, all in non-contact. Now let's crank up the frequency. So he's going to be now not on a 10 or 100 kilohertz, but we're going now really, as you see, on microwave. So we go to a frequency omega p now that is between 1 megahertz and let's say 1 gigahertz. So we're going slowly up in frequency. And this is one experiment that actually colleagues in Sendai, in the group of Jesuit Joe, have done. And you see nicely what they do is actually the following. We apply this kind of microwave voltage to a certain base plate, that's the grayish area here, put the sample on top of it, have a shielding ring on Mars, this is grounded, and then put the tip of the AFM in the center. So what we see actually here is actually the following, that we have a capacitance that actually builds up through this kind of charging of this plate here with respect to the tip. And then when you scan your tip, what you're probing is nothing else than the dielectric constants at that microwave frequency. That's clear. And they do this in this experiment, as you can nicely see here, with two different frequencies. One is actually the linear, and then also they have the second order frequency. So they do a higher order experiment again, simply because they say, as we just discussed, our interaction is non-linear. Why not to track the linear and the higher order experiment as well? There are even more higher orders, but at the moment, for the moment, that's actually what they did. So what do they find as an experiment? So they did some kind of calibration by using, let's say, doped layers. This is an N-dope by phosphorus. This is a P-dope layer by boron. And you see nicely in comparison of this kind of scanning nonlinear dielectric microscopy, SNDM, that's exactly their name they give to this kind of microwave microscopy AFM. You can compare that to a SIMS signal. In SIMS, you're going to destructively reduce, take off part of your surface. You're going to produce steps. The surface here was really produced by growing always 5 micrometer layers of different dopants at different concentrations. And you see here the concentration levels N of what you get here. This is about 5 times 10 to the power 18 and down, down, down again. And then comparing what they have in SIMS and SNDM for both the N-doped and the P-doped allows you to really get some kind of calibration curves, these ones. So you can get calibration on the dopant. Or if you want to put it, you can also measure with this the concentration of any kind of defects in this system. You see the sensitivity is typically different for P and N doped, typically 10 to the power 17 to the power 19, where for negatively doped, it's even less, it's even better. Okay, you can say, well, a certain regime, not too much. There are tons of drawbacks. The resolution is not too bad because actually the capacitance measurements can be really very low in this kind of capacitance. But there's one big drawback. Let me go back, and you can nicely see that already here. The capacitance that you measure in its, so to say, field distribution is a quite nonlinear distribution, as you see. It's not a plate capacitor model that you have really straight lines. This is really difficult, simply because if you want to measure something that has anisotropy, that means the epsilon of the system is not the same along the 3 directions, then you're going to make a convolution out of this. So you're never able really to deduce one of these components alone. So that's one of the drawbacks they have. Nevertheless, they applied this to really some analysis. For instance, on a TEM analysis, they were really looking on these kind of samples prepared by focused ion beam, source, drain, gate. And in fact, yes, they can fit the boron and the phosphorus dope areas exactly to this really 90 nanometer gauge area. So that's one of the big challenges to go for industry with that. So the value they got is really this epsilon of omega. It's only the isotropic value. You can really get, as I just was saying before, the anisotropies of the system, but you get it definitely at this frequency omega. which is microwave. Now let's get higher in frequency. Let's get him enough power to go really for optical frequency or even for terahertz or infrared or even visible range. So we're doing the same experiment by applying the source, and this is my fil rouge encore, but okay, just for symbolizing, this could be also an optical input. But nevertheless, this means simply we are applying, so to say, a bias triggered here by an optically induced dipole. What happens now? So we're going up in the frequency, as you see. We're coming, as we would say, now in the near-field optical regime, where we have naturally now a dipole interaction. So this kind of light that it induces here on my apex of my tip is inducing a dipole, the reddish dipole, and this dipole is a transient dipole. You can turn on the voltage source, you can turn it off, and hence what it does, it induces in the sample an image dipole. So that's basic physics. We're inducing a dipole in the tip, and then actually we're inducing it into the sample. These two start to talk to each other like in a dipole interaction, like we know from magnetism, like we know from van der Waals forces whatsoever. And hence, we see that these dipole forces again are a nonlinear interaction as a function of distance. This is again good, because we can now apply the whole mimic just shown before. That means we can really measure the nonlinearities at higher frequencies simply by using a standard scanning force microscope. The same mimic like shown before, we played again, Sam, here. So that's exactly the point. The tip serves only as the in and out in this case. So it's my antenna coming in, getting out again. So mathematically what we have is the following. We're inducing a dipole into the tip. This means what we need as a physical parameter is the so-called polarizability. So that's not the permanent dipole, but it's quasi the transient dipole strength induced by the external electric field coming in, like my optical radiation or my voltage source here. This dipole talks, as we see, to the sample. Hence, we get a sample response function that is beta, where epsilon s in this function is exactly the sample dielectric constant. And now comes the nice thing. This sample dielectric function can be anything. It can be an anisotropic system. As you see here, this Deka is actually exactly showing that we can have anisotrope in the system. It can be at any frequency omega. And moreover, this sample function can come from any kind of buried structures, that you make layered structures or laterally staggered structures, whatever you want. So this is basically one of the tricks what this type of microscopy has, that we can even look below the surfaces. Now, if you put this back into mass, this simply means that these two guys, the beta and the alpha, they talk to each other, making an effective dipole, an effective polarizability, which is given exactly by this formula here for p polarization. And you see nicely, this is also distance dependent. Pulling back my tip while my optical source is on gives us a different possibility, simply because then the dipole, by pulling back h, meanders into the sample. So we can really probe into the depths of the sample. That's a nice thing. There's more to say. There could be a resonance. We could say, okay, we take a tip, say silicon, whatever you want, or a nanoparticle at the tip, but there's a sample that has phonon or infrared resonances. It's barium titanate, for instance. We want to see soft modes, and hence we can tune either of those, the tip or the sample, exactly to that resonance frequency. So we're not bound to a frequency which is 2 or 3 kilohertz, but we can really change the whole frequency range in order to get this induced dipole interaction on that frequency that I want. I want to have a sample resonance. I want to really see what the sample responds to. Well, this is exactly what you need then for that. You need different light sources. So my AC source here needs to be something like a very huge building, as we have in the Helmholtz Center in Dresden, which means we have a free electron laser there that goes from 4 microns, as you see nicely, down to 250, and we have a second source down to 3 millimeters. So very, very long wave, as you see. But that's exactly what we want. We want to excite the fundamental excitations, the phonons, the magnons, the spinons. And hence, if you're able to couple this kind of excitation to your tip, as we see here, by this kind of dipole-induced interaction, then this is exactly what you need. All the rest is this nonlinear disentangling, as I was showing with the Kelvin, and hence we have, so to say, the possibility to really measure this interaction. Well, in our case, this is possible at room temperature, but also down to low temperatures, and I would like to really show you a couple of experiments and measurements that we did with this, simply starting with here silicon dioxide. Silicon dioxide, an industry sample. You see here nicely we have edges. Silicon dioxide is overgrown, and this wavelength that we apply here, 9.7 microns, is resonant to silicon dioxide. That's why you see it bright here. You see the bright stripes. Oh, sorry, it's resonant to silicon. That's why you see actually it's bright here in the near field picture. You see again what we do the following. We have different near field pictures. We take different higher order modes, 2 omega, 3 omega, and so on, simply to disentangle these nonlinearities. So this first picture shows you that we are sensitive here to the local dielectric constant. There's no anisotropy here in this system simply because the sample is isotropic. And we can calculate the local polarizability of the silicon or the silicon dioxide and hence quantify these values. Second example, a buried system. Imagine that you have a structure that is not really accessible. A scanning force microscope in general is surface bound, but now we do the trick by looking below the surface. So we have again our infrared laser coming in here, and this is basically a sample that is now hit, which is a silicon and a boron doped sample. So we have 100 nanometer depths on top, which was overgrown by simply non-implanted silicon. So in a physical model, what you could say is something, this is like a good sandwich. That means we have something which is really tasty, which is the boron. Well, how can we figure that there's boron there? Well, what we do is we just apply a very simple model, saying we don't know what it is. Well, it could be electronic, meaning that it has electrons that we can excite. It could be phononic, meaning it has phonon resonances which are different from the surrounding, which is my silicon. So we need to sweep through the whole wavelength range in order to really hit somewhere some kind of resonance. So we really blind, we're sticking in the dark, and we really stick our fingers or our tip into the system, and we scan, okay, because we had some hints, between about 10 and about 14 microns wavelengths. And what we find is naturally that at some point we hit, in fact, a resonance. This is not a phonon resonance, but this is a plasmon resonance, because with respect to the silicon, there's enough electrons from the boron that, or let's say holes in that sense, that are really that we have a whole resonance, a plasmon resonance. So that means the tip goes, penetrates into the sample, and measures exactly at these local depths actually how much of these holes do I have in the simple model. And in fact, if we do that, we go and sweep this. Compare that to the theoretical modeling, we see that our experiment is giving us a value of 3.7. The theory says 4 times 10 to the power 19. So the concentration is not badly actually matched for this kind of below surface. Yes, please, 5 minutes. Good, thank you. So we see that we can really have n here, actually, the number density. We took a second example, which is actually shown here. This is a linear, one-dimensional system. These are gallium arsenide sticks, as you see here. And we've been really cutting them down, laying them on the surface, do the same experiment, exactly the same mimic like before. Now we have both. We have phonons and plasmons in this. So we need to do the full fit, not only the plasmons. And hence, by doing this, looking also on the damping constants, we can really deduce the density n of these electrons. We can also effectively measure their mass. And also the mobility mu. This is not really the magnetic moment here, but this is the mobility. So the mobility of these electrons in this small nanowire. So this is all the trick. We need this kind of laser sources in order to really get them excited at the right resonance frequency. So we have this n, m star, mu. Last example. We have also the possibility to go for lower temperatures. That means phase transition. We come back to barium titanate, as you nicely see, where we have here the tetragonal phase. We can go down to the orthorhombic. So, and then basically the lowest phase, the rhombohedral, which we did in 2 different series of papers. And the only thing you have to do now is actually you have to invest into a cryostat and then get your mimic running at lower temperatures. Okay, we did that. And you see nicely that going from 293K into the lower temperature, we have a phase shift. So this is really spectroscopically measured as different function of wavelengths. And then going back, revivals. These resonances are really broad, simply because actually the resonance in the barium titanate is not so small. And also because our tip, so to say, in that case, was not really effectively really responding. It was a broader tip in the sense of having a flat spectral response. But we can really measure the dielectric constant now also as a function of temperature, which is also very important. Just to convince you that this optical method is exactly complementary or equal to what we have really like for PFM, because that's being a standard method now these days for ferroelectrics or for oxide materials. You see again here the out-of-plane polarization of the PFM on PCT001, and you see nicely actually both the A and the C domains. Reddish are the C domains, polarization out of plane, and the blue stuff is all polarization in the plane. Now we compare that, as you can actually see, to the SNOM signal, just actually the way we did it before. And as you see, we did it twice here. We have two different frequencies, lambda 2 and lambda 1. And lambda 1, lambda 2 are only different by about 0.5 microns. And you see nicely also by changing these frequencies, we have a resonance once that is bright here on the C domain, and then we have a resonance that is bright here by changing the frequency on the A domains. So you see already where the phonon resonance is in the A domains for this orientation, S or P, is really pointing at. Comparing that to the PFM signal, this means really enough confidence. These are exactly the same areas, as you can nicely see. Well, I would like, since I have 5 minutes, only skip the superlensing stuff, because that would be a very interesting stuff to go off on negative refraction, which is also a little bit a hinting to what this guy does. What I wanted to show you is actually something where we have so-called left-handed materials, where we have not diffraction that goes on the right side, but goes opposite. And more physically pointed is that the pointing vector and the phase velocity are different directions. This is totally abstruse in the sense of, because ordinary physics, we have always parallel phase velocity and group velocity, which is different for negative-handed materials. I don't want to go into this, but I wanted to close with time, just one thing, one last slide, because all these scanning probes, and that was really the beginning question, can now also go really into very high time resolutions. We can go, for instance, by really adding some more actually of a resolution and time to our Kelvin. So the mimic that I showed to you before not necessarily means we need to measure DC or CV. That means my voltage source here, nicely sitting here, can also be a pulsed source, right? So what happens then? Because then we have a completely different time structure. We're building up something, and then we can measure later. And that's exactly what you see here. You do something, you induce something, and then you measure later by applying a pulse to your cantilever. So what you do, in fact, is pump probe spectroscopy, like Stefan was introducing yesterday, and you had this also last week. But we do this now fully electrically. You see, it's a full electrical pump probe. You can completely do this fully optically, but you can also do both optical pump, electrical probe. So there's tons of possibilities of what you want to probe, and hence, just for that case, for instance, you are able to really track lifetimes of any kind of, let's say, quasi-excitations, which is really interesting. So let me quit with this, with a small summary. So I try to really give you hints on both in contact, but also in non-contact. We have tons of possibilities. The important point is now to really combine your scanning force mimics with frequency. That means actually with excitations at the different AC frequencies. So you want to excite specifically at microwave, you want to specifically excite at, let's say, phonon frequencies, then you have to really tune. What is the future is really time resolved and dissipation, because you saw on the dissipation, there was one slide, there were so many points, and very few have been tracked. But all relies on these nonlinearities, because that's exactly the point. Once we have nonlinearities, we can go for higher order SPM, and higher order SPM is just to bring you back on macroscopic physics. If you get higher orders, that means simply you do the same thing like in a diffraction experiment. You're going for looking on higher order diffraction, and you guys know the diffraction 0 order, first order, second, and so on. At some orders, you become evanescent. So we don't see them anymore. Now, is this good or bad? Well, for us, it's good, because it simply means the K value goes up, and hence the resolution spatial-wise goes up, because that's exactly what is of importance. And with this, let me thank to you. Thank you very much.